Long ago, ancient civilizations existed, whose technology was so advanced that we are unable to comprehend it even to this day. Some say that this civilization had unlocked the mystery of the universe, while others claim it was given to them by aliens from another planet. Among the greatest of these mysteries was that of the pyramid. Were we visited by aliens in ancient times? Nah, it was just some badass engineers that designed this really cool amp that's shaped like a pyramid. Alright, so all kidding aside, I had to do something. This thing's just too cool. So what we have in front of us is a Yamaha Model B6 power amplifier. This thing here is a really fascinating piece of equipment. Now, I'll be the first to admit I've never seen one of these things. I've never worked on one. And really, up until somebody contacted me about this, a friend of mine, well, I didn't even know it existed. So there's not a whole lot of information out there about these, but from what I can gather, this was an attempt by Yamaha at building at least their version of a magnetic field amplifier. So if you go back at some of my other older videos, we do a series on Carver amplifiers. And we talk a lot about the magnetic field amplifier. And really, magnetic field really was more about the power supply in the amplifier rather than just the amplifier itself. Well, this is a kind of a different take on it. And again, any of you who are really into Yamaha or Carver probably may know some of this. And if you do, please share at the bottom of the comments section here under the video. Share some of the comments if you know anything. My understanding is that Yamaha, well, let's back up. So apparently someone originally came up with the design theory for the magnetic field amplifier, or a triac controlled, duty cycle controlled power supply. And apparently Bob Carver of Carver Audio, purchased the rights to use this technology for the power supply in what would become his magnetic field series amplifiers. And around the same time, Yamaha also adopted this technology, but apparently did not pay for the licensing in order to use this. So they made this one amplifier and released it, and it came out in limited numbers, and because of legal issues and patent infringement issues, they had to abandon the project and never built anything again like it. But I can tell you, I just did a little bit of looking at the schematics and some of the diagrams for this amp, and it is very unique and very one of a kind, and it is not a direct copy of the Carver magnetic field amplifiers. As a matter of fact, the power supply makes sense. I could follow that, but looking at the actual power amp portion of this, I'm still trying to figure it all out. It's really, really cool how they did it. I've not plugged this in. I've not tried it. It came in directly from Japan, and it's actually was a Japanese market amplifier. Although I see in the service manual that there were North American and European versions of this amp released that has, and each one you can't modify them, because beyond just the transformer, the whole power supply is different depending on if this runs on Japanese power, European power, or North American power. So you can't convert one to the other from what I'm seeing. This one is the more common one, which is the Japanese market one that runs on 100 volts AC, and it will work on either 50 or 60 hertz. But if we're going to run this here in North America, I will have to use a matching transformer, which the owner of this obtained one and sent it along with this. So we are going to be using that. It's very powerful. It's good at, it's over 200 watts per channel, and the specs on this thing are almost unbelievable. So one of the things we're going to do is see if this thing actually meets the specifications that it was spec'd out at. So we're going to test all this stuff out. I'm hoping I don't have to do a restoration. This is supposedly using rather modern components, very high quality Nichicon capacitors and so forth that probably are just as good as the day that this thing was built. This is not a really super old amplifier. It's probably late 80s technology or something. It's not from the 60s or 70s. So we may not have to do a whole lot to this, or it might be a total basket case. Who knows? But it was advertised, I guess, as working. So let's start out by just seeing if it powers up. And I'll just admit that I did peek inside a little bit just to make sure there was nothing loose or anything. Everything looks tight and looks in place. So we're going to hook this up and give it a try. All right, so we have our 2 kVA step-up transformer, and as you can see, it'll do 100 volt and 120 volt. So it's for converting Japanese electrical system to North American. And I have the amplifier flipped over on its top, and you definitely want to put something soft on your bench because this gloss, you don't want to scratch that. There is a power switch in the front next to those 2 little LEDs underneath. And then turning this around, you have your inputs, you have a ground, you have speaker off button. Yes, you're right, it's not a speaker on, it is a speaker off button. So when you push it in, it turns the speakers off. Push it out, turns the speakers on. And then you have your 2 terminals for your right and left channel speakers. And that's all there is. This is the simplest amplifier there is. And you can see this thing's rated at 100 volts, 180 watts, 50 or 60 hertz. Hi everybody. Thing's so shiny you could see yourself in it. So here's our power light. I have it plugged in over here. And let's see if we can get this thing to turn on. Nothing.
Nothing.
He's dead, Jim. Okay, well I did verify we have 100 volts coming out of the transformer, so we know we have good power. So there is absolutely nothing happening when we turn it on. Well, so much for working as it is. So hopefully it's something dumb like a fuse or a connection that came loose or something. So many years ago when I was in college, one of my electronics professors, for whom I have great respect, said that he was going to introduce a new word, a new term to us, and that term that he was using is the word gunches. What is gunches, you may say? Gunches is an amalgamation of the words great big bunches. So I will use that word from college. This is the first time I've used this word in many, many years in describing how many screws there are to take this apart. There are gunches of screws. And yes, that is an electronics technical term from college that I learned. So without any ado, allow me to start removing screws. And I won't bore you with the several minutes it will take all these out, but you have this up here, there's 6, then you have 1, 2, 3, 4, 5, 6 here, then you have 1, 2, 3 here, then there's another whole set of them inside, and then there's even 4 catch screws inside there, and I'll show you them when we get to them. Okay, so we have that off, and we're still not in yet. But to show you a little extra, so this heat sink, actually the entire pyramid case is made of aluminum, and it's the heat sink. So the whole thing is a gigantic heat sink. And you have 1, 2, 3, 4 screws holding the heat spreader onto the chassis itself. Then you have all these screws around here that loosen this part. Then you have another heat spreader here with 2 screws and a heat spreader over here with 2 screws. And then you have these 4 holes down here that have 4 captive screws to finally release this whole thing. And no, I'm not some genius that's an authority on this amp. This is the first one I've ever seen. But I did download the instructions, the service manual, and they do have a section on how to disassemble this. And reading instructions is a good thing. You know, one of the things I learned in anatomy and physiology is, do you know why it takes 1 million sperm to fertilize 1 egg? Because none of them will stop and ask directions. Okay, 1 bad joke and a dozen screws later, and this thing should be ready to come out. So all we're going to do is we're going to grab this thing by the frame. We're just going to lift straight up. And you can see the whole thing just comes out as one big chunk. And there's your case. And boy, is this thing solid. And you can see the transformer fits up inside here. Somebody got really, really happy with the heatsink grease on there. And so as I was saying, this whole metal piece is the heat sink. And this part here is really thick. You can see these are fins. See how that's designed? And these fins are solid aluminum, and they're part of this casting up here, and then it's all cast into this entire cover. So it says in the manual that this thing can get really warm when running for extended periods of time at high power, and I could see why, because the heat sink is the case. So let's get this out of the way for now, so it's keep it from getting scratched or anything, and we'll move this into the middle of the bench and we'll take a closer look. So I think what we want to do for starters is let's get into here and let's just see if there's a blown fuse or something. Might be something simple. All right, boy, I will tell you, they did not scrimp on the heatsink grease on this thing. Hoping not to get it all over my camera. So there's a big 15 amp fuse, and it is obviously good in here. Your AC voltage is coming in on this side, and looks like the goes out to the transformer is on this side. And here's your triac and your balancing circuit, Opto Isolator, all that good stuff. So everything looks to be intact. So let's just put these 2 screws back on. I'm not going to reconnect the screws to this yet. I'm just going to kind of pop it back on here. And we're going to plug it in, and we're going to see if at least we have the 110 getting out to the board itself. Maybe it's just the switch that's bad, because that's one of those little push button slider switches, and they go bad all the time on other things that I've seen with them. So maybe it's that. We'll see. Okay, we're plugged back into our transformer, and this is just the power cord right here coming straight in. So the power switch actually switches a relay or something on this board. Again, not looking at the schematic yet for this. I just want to see if we just have basic power coming in. So I have the power switch turned off, and I'm going to turn this on. And sure enough, there is power getting into the amplifier. So that means that something on this power supply is not working. If I push this. And the funny thing is, when I go to turn this switch off, I see a little flicker in my light here on the bench light. Almost like that it's trying to do something. So I don't know if... yeah, I don't know. So something strange is going on. I think it's time to get some schematics out. So how many times do we have things on this channel where the owner says, well, when I bought it, the owner said it works and it's fine. And then we get the thing apart and we find out that nothing could be further from the truth. So here we go again, folks. So I've just kind of threw this schematic up on the monitor here, and walking through here, we have continuity all the way out to the SCR. We have continuity through the switch. So this switch takes this line and switches it over to this small bridge rectifier, which I'll show you that here in a minute. You have this IG04080, and you can see it's in this dotted line. This is actually an Scr Driver Module. It's like one of those, you saw me use a similar thing to this. It's an Opto Isolator designed to drive SCRs, and you saw me use a similar thing to this, although more modern, on the electronic circuit breaker project that we did. This is really not an integrated circuit. It is, but it isn't. You'll see this is like an epoxy dipped thing, that little circuit board that was built, kind of put together, if I'm not mistaken. And everything seems to be okay. Now, I didn't apply voltage and test the voltages on these. I'm still going through, if you look here where it says TP4, TP6, these test points, let me show you what those are down here on the board. If you go down, if the camera will cooperate with me here. Okay. Let me lock us in. And let me back you out as you get dizzy from me moving everything around. So, see these little square pads here? These are your test points. And they're down here, 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 here. There's test points. So TP4, for instance, is going to be, I believe, the one that goes into this little bridge rectifier. So the bridge is this tiny little thing right here, and you can see it up here, and there's your AC, and right here is your TP4. So what I've been doing is just kind of looking at the schematic and then identifying it, and then I got an alcohol swab and just kind of clean this off. I'm just going to mark that this is number 4, TP4. That way, when I come back to it, I can remember what they are. Just temporarily, and then I can wipe that off with some alcohol later. But we can actually walk through now and kind of check to make sure we have our voltages. So we have that Scr Drive Module, which, see this little blue thing here? It's the epoxy looking thing. That is the driver module for the SCR. And you have a little SCR, and then you have the big SCR over here. And you have another, you have an Opto Isolator, which is here. You can just barely see it. And if we go up to the schematic once again, it's going to be located, and again, I'm just figuring this out as I go along. That's going to be this thing with the dotted line. So you can kind of see the LED looking thing up here. I think that's what this is representing, this diode, and then you can see the little dotted line to the transistor. So at least from what I can see so far, see pins 1 and 2, 4, 5, and 6. So that's that little yellow thing. So we're making progress on what this all is, and everything so far looks good. So what I'm going to do is kind of get everything into a kind of a safe position where nothing could short out. We're going to start powering this up and look at some of these test points with power now, because statically this is all ohming out. Resistors look to be good. Everything out to this point we have continuity and it looks proper. So we're going to apply voltage and just see what we get at TP4 with respect to this line down here. So our voltage comes in down here, goes around this track, through this coil, and we have continuity all the way to there, into the SCR, out of the SCR if it's turned on, and you can see I can read it there. And then it goes through the coil. So there's two pins here, one here and one here. And if you look, there they are. They go over to the transformer. That's the primary lead, or leads, of the transformer. So if I measure from here to here, I have continuity. So the transformer has a good winding on it. And if I go from over here, go down to voltage, and we should be able to, I'm just going to put a screw in here to hold this real quick. And then, just so this isn't flopping around when we're trying to test it. And then we're going to check some of these. And let me get this thing plugged in. Okay, power is on. And again, we have voltage coming in. And you're really not seeing anything, are you? So let me back up. And I'll move this over just a little bit. So we can get a little bit better view here. And then zoom you in as much as I can anyway. Okay, here we go. So we have voltage here. And I'm running through a pretty heavy dim bulb tester, but there is a dim bulb in there, so if something shorts, it's going to light the bulb up, and hopefully there's some pretty heavy components in here. It won't cook anything on the board. The bulb will take it. But there's enough current, this is a 110 watt bulb, that it shouldn't interfere with the triac if it wants to fire up. So coming through here, through the coil, through here, we shouldn't have anything there, but up on this other end, there's our fuse, other side of the fuse, and that goes to this lead here. And if I go down here, I'm seeing voltage through the coil of the transformer with respect to this, but I'm not reading through here. So there's no complete circuit from here to here. So as a result, this transformer is not firing. So the SCR is not firing. And if I look over here, I only have 200 millivolts on the gate drive. If I go to the other side up here, there we go. I do have drive signal on that side. We see something. But there's nothing on here. So we have to find out why this circuit isn't turning on over here. Let me move back down here. And this little bridge, I'm seeing something on that. And so I should be able to go to DC volts and just see if this thing has anything on it at all. And we got 12 volts. So at least part of this is firing up. Now what we don't know is over here on the Opto Isolator, do we have a bad opto? So from there you can see we have a test point which looks to be, see that test point right there? That's coming straight off of the plus, and it's not showing anything on the schematic for that test point, what it is. So we're going to have to figure that out. Let me take another look at this and see what we're actually looking at. So it seems like the triac is shutting down and not allowing the transformer to fire up at all. So what I decided to do was flip this over and remove this whole module and look under here to make sure, because this is your capacitor bank under here. So there's not much under here except some capacitors and this one little circuit down here that you can see with a capacitor and a transistor. And those kind of provide like a feedback that comes back to that drive circuit. To make matters worse, this is a Japanese version, and the service manual that I have is for the North American and European versions. So there's 3 different versions. I have 2 of the 3, and neither one is the same one that I have. So some of the values here are a little bit different in the power supply. The amplifier is the same, but the power supply reference values are a little bit different because you're dealing with 100 volts instead of 125 volts. In addition to that, this is kind of messy. I've been cleaning up some of the solder joints while I was in here. Some of this is kind of bubblegum looking and is very dirty. And I think this has been serviced before. Like some of these things like down here look like they've been worked on a little bit. Not a lot, but I'm going to clean this up. I'm going to clean off all this messy heatsink grease. There's way too much of it. And just try to clean this up a little bit before I put it back together. Okay, now we're getting somewhere. So you can see what I've done is I've disconnected, here's the wire, I've disconnected the transformer primary from the driver board for the SCR, or I mean for the triac. And I've substituted it with this 60 watt bulb. And you can see the red and black probes are going over to my differential probe for the scope. And basically this should put out a trigger signal, but not, it should be minimum because we're not getting any feedback. So it should keep it from driving hard. So when we turn this thing on down here on the power, you can see our gate pulses. This is directly across the bulb. So this would be what's going into the transformer normally if the transformer were doing its job properly. Now, I do not believe we had that with the transformer connected. So now the question remains, where is our problem? Because that feedback loop is not functioning when we hook that transformer up. It just shuts everything down. So we can see there's something coming in there. Now what we're going to do now is I'm going to try to trace through some of the drive circuits to see where these little pulses are originating from. I'm hoping that the trigger circuit for the little triac, the little driver triac I'll call it, is working. If it's not, that's going to be a big problem because that is the one part that is unobtainium, and you would have to build some sort of an equivalent circuit to substitute that. So that's my next job, and I'll come back as soon as we figure that out. All right, we're making more progress here. So if you look at this waveform right here, and it is right from the fuse socket over to the input of that little triac driving module. And you should see this waveform. And with the dim bulb connected over there, you could see that's pretty much what I have, is that waveform. So I was not able to get this before, and I don't know if it's because I have the transformer disconnected, or I did touch up a few what looked like cracked solder joints on the capacitor board when I had that all apart. But what I'm going to do now is I am going to reconnect the transformer and see if we still have our little waveform. Now, all those noisy zigzaggy lines there, you see how it's kind of noisy right here. It's not a real clean waveform. I have a feeling some of that is that Handtech oscilloscope. This is not the greatest oscilloscope on earth, but for you guys, for me being able to show things on the video, it's really convenient, and I don't really care about that little bit of noise. We're not looking at RF, we're actually just looking at low frequency signals, so I don't really care about that noise. But anyway, let's reconnect our transformer and see what it does. So I am rapidly discovering that this service manual is about as useful as tits on a boar hog. And the reason I say that is this is for the United States model. This is for North European 240 volt. Both of them are different, even with different part numbers, than the Japanese model. For instance, these resistors here, they're calling R413 and R414, but on the European it's 415 and 416. And these capacitors here that are on the triac, in one model it mounts in this position, in another model it mounts in this position, and in my model there's one mounting in this position from here down to here. So there are some pretty substantial differences from what I have, which is the Japanese model, and the other two models. And you can't, I thought maybe I could use this service manual because it was close enough, but when it comes to checking some of these voltages and things and locating the components where you're supposed to test the test points, they are a lot different. And so either I'm going to have to kind of reverse engineer this and draw it out, or I'm going to have to try to find a more accurate set of schematics for this, because this could easily lead you down a rabbit hole if you don't, you know, if there's something that's way different and you don't realize it. So we're going to have to do a little more research here and then come back. Okay, this is definitely not the way to test this, but I've disconnected the primary of the transformer, which, remember, it has a maximum input of about 18 volts. And this is one of those magnetic field transformers, I guess we'll just call it that. So it's really not designed to run one-to-one like a normal transformer. But I have this connected to the variac, and I'm looking at the current draw. What I noticed was if I even put 1 volt AC on here, the current would shoot up really high, like 2 amps. And if by the time I got to about 5 volts, it was almost 11 amps, meaning that there was a dead short somewhere. So I disconnected the secondary windings of the transformer from the power supply board. And these two red wires represent the plus and minus 80 volts. So there would be 160 volts between those, with 18 volts going in here, roughly. And as soon as I do that now, with no load on it, you can see it just shoots right up. I have all kinds of voltage, and there was no voltage originally. So that led me to think, well, okay, what does it look like where those wires would have been connected? And if we go here and here, let's see if I can do this around the camera. Probably not. There we go. Can you see over there? 0.23 ohms. There's a dead short. That's probably a bad bridge rectifier. So there you have it. And of course, you can't really measure that sort of thing with this winding out there, because this winding has a very low DC resistance in and of itself. So you really have to disconnect it. So I've reconnected this transformer just to keep you up to date here. And I was able to get the same signals, drive signals. And they're just tiny little pulses trying to start the thing up, and it can't start up, that I was getting with the dim bulb tester. So without that feedback loop from the transformer, it could never increase its frequency or anything. So that's why the dim bulb would work, but you wouldn't get any drive into it. It needs that feedback loop to drive this little driver circuit. So now we're going to go up here, and we're going to hopefully find a bad bridge rectifier. So then, after taking all this apart and removing this big bridge rectifier, I found out it is in fact still good, and the short was still there, and the only thing connected to that same place was this little wire, which leads over to here, which led over to this little bridge rectifier. And it, in fact, is dead shorted across the AC inputs. And you can see this is a factory bodge job here, by the way. This is not something that somebody came in and did. They cut a track over here and bodged this resistor in there. This in the schematic is only like a 2.2 microfarad. They changed it for a 47 microfarad capacitor. And I think this has something to do with the time delay circuit, and they modified it at the factory, and this is the way they did it. I actually cleaned this up a little bit. It was horrible. It was like bubblegum solder on there. It was pretty bad. So we're going to replace this with an appropriate replacement, and then put it all back together and see if it perhaps will work this time. So I physically have a bunch of these, actually, these little ones. They're exactly the same case. However, when you look on the schematic, that little bridge, which is right here, is directly across the two red wires, which happen to be the plus and minus 80 volts, which means there could be, you know, from center tap, so there could be 160 volts RMS across this. I think these ones are only rated at 50 or 100 volts. So I'm a little bit nervous to use these. Now what I also had was just a slightly different case and slightly larger size. You can see they're not much larger. One of these. And it's rated at 1,000 volts at 2 amps, which is way more than we need. But we have enough room on the top of the board to mount it. So I think that's what we're going to do. Just better safe than sorry, because I'm just not sure what the rating is on these, and I would not want to put a 50 volt bridge rectifier in where we're going to have 160 volts potential. Yes, and in addition to the shorted bridge rectifier, the little transistor is bad as well. So we're going to replace that with a KSC 1845. Hopefully that'll fix that. Probably might as well replace the diode and the capacitor while I'm in there for what they cost. One thing leads to another. All right, I think I got everything in shot, because if we get big boom, we want to catch it on camera. So I got all those parts replaced, put everything back together, put all the wires back onto the boards, and well, let's turn this on. And now let's turn the power on and see what happens. Hey, red lights. And big drive signal. Look at that. That is much more than what I would expect. And the protect light went out. So the amp is up and running. Excellent. So I pretty much gave up on trying to find the right service manual for this, because it would be the Japanese version, it would be written in Japanese, and it would obviously only be over in Japan. And really I couldn't find anything online like that. So I just decided to to wing it, and well, we stumbled across the problem. So let's test it out now and see how this thing works. Okay, I have the amp turned on, and we're going to check the power supply. And they want us to check from over on the transistor, so they're showing just this pin of this transistor, which this board is looking from the top side, so it's flipped over. So it's actually going to be on this side. And we get on here, and it's supposed to be 76 volts plus or minus 200 millivolts. I'll call that close enough. I'm not going to mess with it. If it needed adjusted, we would adjust this pot right here. And then this pot is for our center point adjust for the Opto Isolator. And the way we measure that is go between these two test points, and it should be 60 millivolts plus or minus 10 millivolts. And it's 61 millivolts, so that's perfect. I didn't have to touch that at all. Really, they were right on. So we didn't have to touch anything there. So power supply is good. Now we can actually look at some of the amplifier adjustments. Okay, it's been about a week since I've messed with this thing. And yes, my voice is a little different. I'm just getting over a little bit of a cold. It really hasn't slowed me down any, but just annoying because it's in my sinuses and making me talk like a frog. And no, it is not the infamous illness that is going around right now. Although, out of an abundance of caution, there's been a lot of places closed down or limited hours and so forth, which I think is a good thing until we get a grip on how whatever that is spreads around and so forth. But anyway, enough about that. I'm rapidly coming to the conclusion that this thing is one of the more difficult amplifiers I've ever serviced, and not necessarily because of the kind of the different circuit design it uses that's unique, but really because of the way they put this thing together. They make it very difficult to test the amplifier while it's powered up, because you really have to put everything together to power it up. And when you put everything together, certain parts of this amplifier are blocked from really being able to get to it. In other words, you can't get to the back of this circuit board because the big power supply is on top of it. And if you separate them, the wires aren't really long enough to fit properly, and everything's kind of exposed and could easily short out. So you have to be really careful. And to make matters worse, the circuit board really doesn't have very good screening on it, so it doesn't really show you the component numbers on the board. So you have to go with these things, which, you know, when you wear progressive lenses on your glasses and everything, looking at these tiny little things is not always the easiest thing on earth. I'm sure some of you can relate to that. But to find something, you kind of have to locate it on this map. Then you have to go over to here and try to find it, and then go ahead and test the part. But the problem is, for instance, these two little preamp modules, the actual pins, there's only 4 or 5 pins that all the signals for this board and this board go through. But those pins are buried down in here and buried down in here. There's no possible way you can get on them except from the back of the board, which is covered with the power supply module. So really, and the problem I'm having right now is the DC offset adjusts perfectly. We can get DC offset, but both channels are very, very limited in the bias. In other words, you can't adjust the bias level to where the instructions require it. As a matter of fact, you have almost no bias adjustment at all. It's very little. So what little bias you have, there's enough to measure DC offset and to zero that out, which is fine. But when it comes time to increase the bias, it does not work. And both channels are doing the same thing, so I suspect it's something power related, but we really don't know yet. Moreover, I believe there is a problem because looking at this protect circuit, here's your protect relay, and it's kind of neat how they did this. Here's the coil for the protect relay. It goes out to the speaker switch. So when you push the speaker switch, you're just killing the protect relay is all you're doing. You're preventing the protect relay from pulling in, and your protect relay is right here. This is your speaker output, and you can see one there and one there. Those are your speaker outputs. So really, all they're doing is dropping out the protect relay when you push in that button, because it just, all this does is take away the ground or the common point right here from the relay coil. I cannot get this relay coil to come in, and I can't, it's really difficult to get in here to check these voltages, but I have a suspicion something is not right with one of these voltages here, and we're getting we're holding this relay from coming in.
Now, that's not why we're not being able to get bias. I think we're not able to get bias because of the problem that's keeping this from coming in, if that makes sense to you. So that's really what I'm focusing on. But I really need to come up with a method of being able to get in here and test this stuff with the amplifier turned on without shorting things out. I can kind of see why Yamaha abandoned this project beyond the whole copyright thing. And even with that, I look at this, and although there are many similarities to the Carver type magnetic field power supply, to me it almost looks different enough that if they wanted to fight that issue, they could have. I think maybe they just used the copyright thing as an excuse to abandon this project. You have to remember, Yamaha at the time was putting out some amazing audio equipment when this thing was built. And I'm sure that equipment was every bit as good or better than this, even though it was larger and conventional, had linear power supplies and all that. Yamaha was really putting out some top-end gear. So this probably was more of a novelty to them. And I don't think they ever kept in this product line enough to perfect it. So at least that's what I'm guessing after looking at this thing and what it's like to work on it. And you could see all the extra components that they never used that maybe they had intended to use at one point in time on the board. Who knows? Not to mention, this is the Japanese version, and there may be some slight differences, again, as I've found, between this one and the North American and European versions. So anyway, I've talked enough on this. Let's look and see what we can find. As soon as I find the signal that I'm missing or that's incorrect, I'll come back. So I'm trying to make a little sense of all this, and I took my colorful markers and kind of traced out the voltages. So you have a high voltage rail and a low voltage rail. The high voltage rail is positive and negative 76.5 volts, and the low voltage rail is positive and negative 36.5 volts. Now if we go on to TR145, we should see the high voltage rail on one side, which is 76 volts, which is on the emitter, and then on the collector we should see 36.5 if the amp is sitting at idle, because your 36 volts, this is a lot like the Carver in some ways. Here's your steering diode for your low voltage rail. It's coming in and it kind of bypasses all of this, and then this will come in as this bias is on, and it's turned on. Ooh, she just kicked on. Smoke! Look at that. Nice. So it was working. I was going to show you the non-voltage that was on there. Now there's really no voltage on there. Well, I'm pleased to inform you all that the circuitry protected the fuse. I was worried about that. So now we got to find out is what caused the smoke. I feel a little warmth over here on these transistors, but nothing else really looks cooked as per se. It's just amazing how much smoke can fit in such a tiny little thing. So this is the little driver triac that drives the main triac, and for whatever reason it decided it was going to give up its smoke. And I don't have any of these little teeny tiny triacs, but I do have a sensitive gate triac that should work for this, but it's kind of like driving tacks with a sledgehammer. I have one of these in a much bigger case, but it will work because electronically it should function in this position. So I just mounted that in there. Now I still have to measure this to see if it's good. You know, the main triac, maybe it crapped out as well, but yeah, this is one of those really wonderful amps to work on. So here I think is all the cause of the problem, and it's a 2SC1815 which is just a normal NPN transistor, but when you test it, it says it's a Darlington, and it shows you emitter, base, and collector, but then it shows you that, and that, and the bottom line is, if you look on the schematic, and I looked up 1815, it's just a standard NPN, and that is directly in that feedback loop for the driver for all this. This is your voltage detection. Now that probably has been messed up for a long time, and that's what's causing all this not to regulate right, and it's causing this to go crazy, and that's what shorted this out, probably from that feedback loop. Hopefully that didn't damage this. If this is damaged, we're in a heap of trouble. But I can't see that it is, but we'll see. So here's to all of those who say you never need to recap these older amps. The caps are good, they don't go bad, you're just wasting your time. Well, there it is, dead shorted cap. And I can tell you now, I can see that because if you recall, look at the history that we went through troubleshooting this. This bridge was shorted, which actually charges these two caps. The triac blew. The thing worked for a while, and then while we were just sitting there watching, it blew up. The smoke came out. And what happened was this capacitor had very high ESR. It was bad. And probably this other one's bad as well. I haven't pulled it out yet, but I've desoldered it. But it's probably not much better. And so that makes quite a case for recapping these things. Yep, look at that. This one only has 1.7 mega ohms of resistance. And it should be much, much higher than that. So even this cap is probably bad. If we put it on the capacitor analyzer, I'm thinking we got two bad caps here. Let's take a look up here real quick. That one's reading yet. This is an 80 volt cap, and I'm only on 50 volts right now. If we go to 100, this is a little bit overrating the cap, but it's never going to come out. So it's even getting a higher ESR. So chances are they're probably, now these Nichicons, there's a possibility they're still good, I hope, but these definitely need replaced. I don't know if I have anything 3300 at 80 volts, but well, we'll take a look and see what we have. Well, I guess this video is going to be a two-parter because obviously I don't have any capacitors anywhere near these values, so I'm going to have to order them, which is going to take several days. But I think in this part we at least found out the secret of the pyramid. We've always wondered what's inside of the pyramids, and well, from what I'm seeing, it's smoke, and it escaped from this one, so we have to go put it back in. So that's what we'll be doing on part 2, and I'll get this video edited and posted, and stay tuned for the next one where hopefully, no promises, but hopefully we'll get this thing working and we'll actually get to see how it works and listen to it. So as always, I wish you all peace, joy, happiness, and good health in your lives. And I know with the current situation, wishing you all good health has a little bit different meaning, but I wish the best for all of you. Stay well and take care, and we'll talk to you all soon. Bye-bye.